Welcome back. Our previous video introduced the conditional choice probability estimation approach and briefly overviewed some of the key ideas and things that we need to keep in mind if we want to implement this method. The main idea is that we can avoid solving our dynamic discrete choice model using backwards recursion if we want to estimate the parameters of our utility functions. In this video, we'll go through in depth the math that gets us this clean estimation approach. And the key feature of this Hotz-Miller 1993 paper is that this CCP estimation approach works for any distribution of our epsilons. However, it's most easy to implement using the Logit model, which we'll also cover. So even though the formulas are simplest for the Logit model, the general idea applies much more broadly. This is the title page of that famous paper in the Review of Economic Studies. And Joe Hotz was one of my dissertation advisors, and Bob Miller was a frequent co-author of both Joe and another one of my advisors, Peter Arcidiacono. And this paper is introducing this CCP estimation approach, but then also applying it to fertility decisions, and in particular, whether a couple wants to stop having kids completely. As we talked about in the prior video, the key insight here is that these differenced conditional value functions can be mapped into conditional choice probabilities. And the main estimation method is that we extract these CCPs in the first stage of our estimation using data, and that we can use this to avoid solving the backwards recursion problem. And as I mentioned earlier, this application is on fertility decisions among couples, and this is a classic case of an optimal stopping problem. So let's start by thinking about a person with two choices and with the errors distributed type 1 extreme value. If we just write out the formula for the probability of making choice 1, this is the familiar Logit probability formula, and what we can do is we can think about writing a similar formula for P0, and then taking the ratio of them. The denominators will cancel out, and so we're just left with the ratio of the numerators, which we can then express as the exponential of the differenced value functions by properties of exponential functions. This is, you can think of this as the other edge of the independence of irrelevant alternatives sword. So on the one hand, IIA is imposing very strong assumptions about how these options are substitutable. On the other hand, it's greatly simplifying computation to make that assumption. So there's pluses and minuses to every assumption, and it's very clearly front and center what's happening with this IIA assumption. Then we can take logs of both sides of this equation, and then we get a very simple formula for the differenced conditional value functions. It's just the difference in the log probabilities, or the log of the ratio of the probabilities. Those are equivalent. And the key thing here is that this works for any two alternatives in the same way that the IIA assumption imposes that the ratio of the choice probabilities is only a function of the value that those two alternatives provide, and not any other alternatives. So again, this is like, we got the IIA, it's a very strong assumption, but in this case, we're leveraging it for simplicity's sake. So now let's take a different approach. Let's look at the formula for capital VT plus 1, if we again assume that the epsilons are type 1 extreme value. In an earlier video, I showed you the Bellman equation, and we saw that it had this recursive structure. So we can write the Bellman equation as the Emax of the conditional value functions plus the current period epsilons. So this is for period t plus 1, but this is true for any time period. And if we assume type 1 extreme value, then we know that the Emax term has this convenient closed form log of the sum of the exponentials formula, plus Euler's constant, that's the C there. And if we do some algebra, we can show that big Vt plus 1 is equal to little Vjt plus 1 minus log of Pjt plus 1 plus Euler's constant. And we can write this out for any alternative j. So we'll walk through that algebra right now. The key trick, which is convenient in many mathematical derivations, is to multiply and divide by the same number, which is equivalent to multiplying by 1. And then that allows us to kind of regroup different terms, and then we can get a different formula that's more convenient. That's what we're going to do here. We can multiply and divide by the exponential of vjt plus 1, and then we can bring that denominator of this new term that we introduced into the summation. And what does this second component of this product look like? Well, it looks like the inverse of a choice probability. And if I have a log of an exponent times another term, I can break out that log into a log of an exponent of this plus a log of this, right? So that's what we're going to do. This first term simplifies to just vjt plus 1 because log and exponent are inverse functions. And then this log sum term turns out to be, let's take the log of 1 over pjt plus 1. Then we can simplify this further by noting that the log of 1 is 0. So then we get that big vt plus 1 is equal to little vjt plus 1 minus log of pjt plus 1 plus Euler's constant, and that this is equivalently true for any option in our choice set. So if we go back to our earlier derivation, we saw that the difference vj's was equal to the difference log probabilities for those options. And we're going to define this mapping, this log of the difference probabilities. We're going to call that mapping psi. And we're going to use a superscript j to be the first term in that mapping and the subscript 0 to be the second term in that mapping. So we can do this for any j and j prime that we want. In the Logit model, this is going to be called our inversion formula because it's going to allow us to express the difference conditional value functions, which are objects of our structural model, in a form that only depends on the data in terms of these choice probabilities that we can see in the data. So if we did the regular approach with the backwards recursion, we'd have to solve for these difference conditional value functions, then use those to get the policy function choice probabilities, and then estimate the parameters from there. With this inversion mapping, using this psi, we can just look at the pj's in the data and the p0s in the data, and then from there we can directly recover the difference conditional value functions and then just estimate our parameters from there. We don't have to solve the model. So Hotz-Miller have a proposition in their paper where they prove that this invertible mapping, this psi function that maps from the conditional choice probabilities to the difference conditional value functions exists. And so I'm going to walk you through what that looks like, or what the end formula looks like more generally. So let's just consider option 0 just for the sake of example. So we can also, if we were writing out the Emax term more verbosely, we would write it out as big Vt plus 1 is the Emax of each of the little Vt plus 1s plus their associated epsilon. So this is just a slightly more verbose way of writing out that Emax formula. And what we can do is we can pull this V0t plus 1 out of the Emax because it's not random. The thing that we're taking the E over is the epsilons, not the V. And then we can just subtract V0t plus 1 from every component of this maximization. So this is just simple algebra. I'm rearranging terms. So we get this equivalence between these two lines just by bringing the V0 term out. Then we can replace these difference conditional value functions with their appropriate psi functions. And in particular, these might be a function of all the choice probabilities. So we're not subscripting the p's, but the associated probabilities that they're a function of are indicated with the superscript and the subscript on the psi function, like I introduced earlier. So all we're doing here is just changing those difference to conditional value functions into this psi function. And this is just highlighting that dependence or that equivalence. So according to this proposition that Hotz-Miller proved, this mapping psi works for any distribution of epsilon. It just may not have a closed form for some distributions of epsilon, which we'll get into in a later video. So that's the key idea of this Hotz-Miller inversion approach. Our next video will apply these principles to the empirical example that Hotz-Miller went through, which in this case is a model that has a terminal choice, meaning that once a certain choice is made, there are no future choices after that. And the key idea is that this terminal choice is going to allow us to unravel or dissolve the recursive structure of this dynamic programming problem. So I hope that you'll look forward to that video and that I'll see you there.